Hello, am I audible? Hello, Sucheta, am I audible? Hello, am I audible?
Yes, sir, audible.
Okay, okay. So let's start. So, yeah, yeah, yeah. So is it visible? Yes.
Yes, sir.
Okay. So last class we are in between size exclusion chromatography. So we are talking about different chromatographies. So already we have discussed gas chromatography, HPLC high pressure or high performance liquid chromatography, and ion exchange profile, etc. So size exclusion chromatography, SCC, we can see as SCC is called gel filtration or gel permeation chromatography. Uses porous particle to separate the molecules of different size. It is generally applied to large molecules and molecular complexes such as proteins, industrial polymers, etc. When an aqueous solution is used to transport the sample through a column, the technique is known as gel filtration chromatography. When aqueous solution is used to transfer from simple molecule. When an organic solvent is used as a mobile phase, the technique is known as gel permeation chromatography. The separation of molecule is called fractionation. Size of force in bits of determines the exclusion limit. So what is the principle of size exclusion chromatography? A mixture of molecules dissolved in liquid. The mobile phase is applied to a chromatographic column which contains a solid support in the form of microscopic spheres or bits. The mass of bits within the column is often referred to as a column width. The bits act as a trap, shapes and function to filter small molecules which become temporarily trapped within the pores. Larger molecules pass around or excluded from the bits. Large sample molecules cannot or can only partially penetrate the pores, whereas smaller molecules can access most all pores. Thus, larger molecules elute fast, smaller molecules elute later, while molecules that can access all the pores elute last from the column. Larger molecules elute fast, smaller molecules elute later. Larger molecule will remove from the system first, then smaller molecule. While molecules that can access all the pores elute last from the column. Particles of different size will elute filter through a stationary phase at different times. So this is the total phenomena of size exclusion principle. Here, particles of different size is separated one by one. So listen, these are the principles where we take a different volumes of solvent. Heat is the total volume occupied by the packing in the column. P is the volume of solvent in the pores. P is the free solvent of solvent. So these are the different components present in size explosion. First is stationary phase. The mobile phase, the mobile phase, the columns and the columns etc. So stationary phase as all the chromatography contains both stationary phase and mobile phase. So we'll use a column and another is form or detector. So in stationary phase, we'll use semi-permeable porous beads with well-defined range of pore sizes. Beads are cross-linked polymers. Degree of cross-linking is controlled carefully to use different pore sizes. Degree of, degree of cross-linking is controlled carefully to use different pore sizes. Smaller pore size are used for rapid desalting and proteins or protein purification. Intermediate pore size are used to separate relatively small proteins. So very large pore size are used for purification of biological compounds. So stationary phase used for gel extrusion chromatography include dextran, polyacrylamide, dextran polyacrylamide, etc. Each is available with a variety of different range of pore size in the bits. So listen, so these are good stationary phase should following properties. So stationary phase should have the following properties. It should be chemically inert. It should be inexpensive. It should not react with component to be separated. It should not react with the EUT. It should be colorless, uniform in size and shape. So it will be mechanically stable. So these are the good polar highly rigid gels classes are so that's nothing but a homopolysaccharide of glucose base. It is prepared with various degree of cross-linking to control oxide. The spot are dry bits, the bits, and water layer. The trade name is Sepalex. It is mainly used for separation of small peptides, globular proteins, small to abnormal molecular. So these are the different ranges of molecular models. So the typical separation ranges that can be achieved using separates are given below. Molecular ranging. So these are G10, G15. These are the depending these separates used for the range of molecules. Polyacrylamide. These gels are prepared by cross-linking of acrylamide with N-methylyl bioacrylamide. The pore size is determined by degree of cross. The separation properties of polysaccharide gels are mainly the same as the they are solid as bioavailability. They are available in wide range of pore size. Agarics, linear polymers D-galactase, T6 anhydrogalactase. It forms a gel that is held together with hydrogen bonds. It is dissolved in boiling water, forms a gel when it is cooled. The concentration of material in the gel determines the force. The pores of agar or gel are much larger than those of saccharide. So useful analysis for separation of large globular proteins, long layer molecules such as DNA. So what are the mobile threads? The liquid used to dissolve the biomolecules to make the mobile thread usually called. The liquid used to dissolve the biomolecules to make the mobile thread is usually called the matrix of biomolecules dissolved in the buffer. Instead of biomolecules dissolved in the buffer is called sum. The choice of mobile threads to be used in any separation will depend on the type of separation to be achieved and component to be selected. The most common elutant in the polymer that dissolve at room temperature: tetrahydrofuran, chloroform, dimethyl formamide, etc. So what are the mobile threads? Synthetic elastomer polypeptide would use toluene as a mobile thread solvent for PS, PVC, styrene, tetrahydrofuran, polyurethane, dipolyethylene. So 14 for police water and unit for. So different solvent selection will be taken. The solvents used for mobile phase of ACC are limited to the following criteria. The solvent must dissolve in the sample completely. The solvent has different properties with the solute in the eluate, typically with solvent attracting. The solvent must not degrade the sample during use, otherwise the viscosity of the runtime of capture. The solvent is not corrosive to any components of mobile phase filters. High purity of solvent is recommended. Filter mobile phase solvent using 0.5 micron filter to remove any particular dust. Antioxidant is used to fry or benzene to keep solvent stable in high temperature. Other additive eliminate absorption interactions solved with column material used for cycles. So how we prepare the sample filters? The sample solutes are supposed to be prepared in dilute concentration less than 2 mg per milliliter. A good solvent can dissolve a sample in any proportion in a range of temperatures. Samples with broad molecular weight distribution may require higher concentration. It is recommended to filter the sample solution before injecting into columns in order to get rid of following. So what are the columns used? So we use analyte column 7.5 to 8 diameter, refractory column 22 to 25 diameter, usual column length 25, 30, 50, 60 centimeters length will be equal to narrow bore column 2 to 3 diameter in selecting single electron column. Shorter columns save time and solve. So it will take shorter columns. That will save your time and solve. Small particles, typically 5 mm, provide a better resolution. On the other hand, 5 mm of even 3 mm packing are more sensitive towards contamination by samples containing particles as larger as 20 mm might be recommended for very high molecular weight. Smaller particle size packing can sometimes result in shear degradation of larger polymer because the space between particles varies. Columns with a different porosity, mixed bed columns provide a better support. Handling of size explosion chromatography. The columns Second, size exclusion should be always run in the same way. Side exclusion columns should never be operated in a backward direction. Care should be taken in connecting columns or in sample index. Replacing a closed inlet field to the interior suppressor which can reduce column. So these are some handling for person of size. So this is the tab. Column size exclusion column. So in this this is the mobile file, this is the camera. So the something will ingest here and this is the column and this is the here. Look at it. From a high constant flow rate has to maintain during the entire chemotherapy. So this is very important. This range of flow rate only 0.1% can cause an error in molar mass of the most bombs can also reproduce the flow rate directly. So types, series from, prescription from, etc. we can test. So whatever detector concentrator sensitive detector, bulk property detector, refractive index detector, shallow property detector, ultraviolet absorption detector. So these are the different detectors. So what are the advantages? Not analysis, well-defined separation, narrow bands and good sensitivity. There is a no sample loss. Small amount of mobile is but the flow rate can be. So these are the advantages in size exclusion. So what are the disadvantages? Limited number of peaks that can be resolved within the short time scale of peaks. Impression must be performed before using the instrument to prevent the further. The molecular masses of most of the chains will be too close and different. So these are the advantages and these are disadvantages. So where will apply this size exclusion? So in proteins fractionation, in the purification, molecular weight determination, separation of sugar, proteins, peptides, numbers, other on the basis of that. This technique can be determined the quaternary structure of purified protein. So size exclusion chromatography is widely used in for desalting and co-operation. So these are the different applications of yes, size exclusion. So go to next go to mem- membrane separation. So membranes are already we have discussed different separations, gas chromatography, ion exchange profiling, chromatography, size exclusion chromatography. So these are the different separations. Also, a membrane can separate the mixture of compounds. So here we'll talk about membrane separation processes. So membrane processes are an accepted unit operation for a variety of separation in chemical and food industry. The processes are driven by pressure, concentration, electric force, across the membrane and can be differentiated according to the type of the reinforced molecular size type of process. Basic unit of membrane separation process is membrane. Membranes are semi-permeable membranes, that is the barriers used to separation of two phase. One is permeate and a retainment on the basis of particle size and electric charge. It performs separation by a combination of filtration, purification, sieving, and diffusion. A separation efficiency is usually affected by different process factors like fuel composition, pH, temperature, pressure, etc. So what are the principles? Listen, we have a solvent here, we have a solute particle. So through the membranes, the solute will pass through, and this is the solute solvent mixture. So through the membrane, the solute will pass through this permeate. So the separation is accomplished with the application of driving force on the solution of the fluid to pass through a separation specific membrane. So in the membrane separation process, the fluid the fluid stream is separated into two fractions. Permeate, the fraction of fluid that permeates through a membrane is called permeate. Retinate, the fraction of fluid stream that is retained over the two membrane is called retinate. So these are the two forms used in two terms used in a membrane separation. One is permeate and another is retinate. So what are the types of membrane used? Most commonly made of organic polymer and inorganic polymer. So organic polymers like cellulose and its derivatives like polyamides, polyolefins, polycarbonates, polysulfones and chlorine etc. is used for organic polymeric membrane. Inorganic membrane based on oxides as silicon, zirconium, calcium. The principal requirement for membrane are high permeate flux, chemical stability and inertness, good mechanical strength, thermal stability, good retention capability, smooth fouling resistant surface, resistant against microbial action, affordable cost, long service life. So these are the different requirements to be a membrane. So membrane हवा पाइप, these are the different requirements. You can see on the screen. So there are long service life, our affordable cost should be affordable cost, resistant against microbial. So these are the different requirements to use a membrane. So most of membrane filters. So membrane filters tend to be dead end and cross flow. Dead end field flow is perpendicular to the membrane surface. This is called a large reduction window. Cross flow of solution is parallel to membrane surface. Flow causes turbulence, produces shear. So then this is the different factors controls the membrane process. So based on driving force, the membrane separation divided into different parts: pressure driven membrane, potential driven membrane, concentration driven. So in pressure driven membrane, microfiltration, ultrafiltration, nanofiltration, reverse osmosis. So these are the processes involved in pressure driven membrane. Potential driven membrane electrodialysis, electroosmosis, concentration driven memory. So based on the size of material, so these are the different classes. So microfiltrate, microfiltrate, ultrafiltration, nanofiltration, reversal. As we have discussed, depending on the time and we have different filtration. Under the pressure general memory, so we can see different categories of memory. So these are the micro sensing to membrane different microparticles to set up. Microfiltration is a low pressure cross flow membrane process. Low pressure and cross flow membrane process. Microfiltration designate a membrane that is separation process with a larger membrane separates the fully colloidal suspended particles in the range of 0.05 to 10 microns. It is used for bacteria removal, fermentation and food clarification and measurement. So this is microfiltration application. So microfiltration applied to food industry. Clarification of beer, wine. So we can clarify the beer wine for different microfiltration process by using membrane process. Microorganism removal of oil, droplets, dark chlorine, removal of suspended solids, fats, aseptic filtration. Application diabetes. So in diabetes, inspirability, bacteria, removal of bacteria from meat, treatment of cheese. So these are the different applications of microfiltration in food industry. Ultrafiltration. Ultrafiltration is a electric extraction. That operates low pressure up to 10 bars. Ultrafiltration lies between microfiltration and nanofiltration. So these are the different or depending upon the size the molecule or bacteria. So size is 0.1 to 0.0. Ultrafiltration allows for the concentration of polymers like polyester, polyamide, are removed or eliminated, whereas that numbers inside they tend to overcome. The concentrated milk is used in manufacture of many types of cheese. At the same, the ultra is become the bread, so this is formulated water that minerals, pressure would apply. So here two membranes it will filter here. So what protein concentration depend on is a regulate is used to promote performance. So nanofiltration, here both sides will say very smaller 0.1 to 10 nanometer, that is 0.001 micrometer, 0.01 micrometer. The mass transfer mechanism in nanofiltration. So these are the different sizes in nanofiltration. So nanofiltration is used to remove mainly monovalent ions, partly demineralization of water. Nanofiltration can perform these are the so even reverse RO system, the reverse osmosis. It is a membrane separation process driven by process gradient in which the membrane separates the solvent from other components of the solvent flow is opposite to the normal osmosis. Mostly from low concentration to high concentration to a semi-permeable membrane. So these are the mechanism of different reverse. We can see and here we apply pressure at 30 to and the reverse reverse failure for more concentration. So water or concentration solution in osmosis high concentration to reverse osmosis. So, so what are the advantages in membrane separation? For this, so separation streams and components at a lower temperature minimize thermal damage to the product. Separating the component in synaptic form, less energy use, easy to operate, environmental safe, it does not denature the proteins, no requirement for chemicals, can remove 90 to 100% of pathogen from the water. Allow. So these are the different advantages of the main separation. Frequency and disadvantages. The main disadvantage of membrane separation technology are turbid water cannot be used, there may be risk of bacterial abundance, gas filters breakable can break quickly, the membrane filters can crack easily, only liquids are sterilized by this method, filters are costly to repair. So these are the different disadvantages of application. In industry and laboratory, it is used to stabilize the labile fluid method. Most effective acceptable method for filtration of fluid. In the pharmaceutical, cosmetic, electronics and food beverage industry, they used to monitor the steps. So also it is used in water, wastewater. Again, it is used in food sterilization, beverage industry, pharmaceutical industry, used to separation of milk fraction, used concentration of protein, used to defense. So these are the different applications of membrane separation. So RO, NF, UF, NF. So these are used. You can see in a water filter. This term will be written. So these are nothing but separation of solute through a membrane. So membrane separation technology serves alternative for various conventional methods. So these are the preparation of separation through membrane. So you can see. Let's move forward to another separation method that is electrophoresis. So another large separation is electrophoresis. So what is electropolis? Electropolis is nothing but a separation by presence of electric field. So with application of electric field, separation is occurred at electropolis. So in this one, meaning transport by electric. So electricity forests means movement. So common electrophoresis is a physical analysis which involves separation of compounds that is capable of acquiring electric charge. So electrophoresis may be defined as the migration of the charge particle to some source of influence of an external electric field. So electrophoresis may be defined as migration of charge particle. So we have two primary cathode. When cathode anode is active, when we switch on the switch and the molecules separated. Some will go to the cathode, some will go to the anode. So this separation is not as that are suspended between two electrodes tends to travel towards the electrodes that bear support. Means positive charge goes to the receiver, negative charge goes to the positive electron reach and not negative electron towards cathode. The positive charge will go towards anode. So electrophoresis is the movement of charged particles through the electrolyte when subjected to pressure. So you can see that electrophoresis is the movement of charged particles through an electrolyte. Like sodium chloride, potassium chloride, whatever, and it is subject to cations move towards cathode, anions move towards anode. By this technique, solutes are separated by their different rates of travel through an electron. So commonly used biological analysis, particularly the separation of proteins and fats. So we will use electrophoresis for separation of protein, separation of mixture of amino acids, separation of peptides, separation of lipids. So what are the factors that will affect electrophoresis? Net charge on the particle. So particle का net charge क्या है? That would be positive or negative. Mass and shape of particle. So what will be the mass and shape of particle? pH of medium. So pH medium will demonstrate how particle charge species depends on the pH of solid. So strength of electric field, properties of supporting medium, and so these are the different factors which affect the efficiency. Any charge ion molecules migrates when placed in a electric field. The rate of migration depends upon its net charge, size, shape, and applied energy. So any charge ion or molecule, what are the principles? And the same principle, charge ion or molecule migrates when placed in a electric. The rate of migration depends upon the net charge, size, shape, and applied energy. So that can be explained in a equation. Velocity of molecule is equal to E P by S. So E is where electricity, Q net charge of the molecule, F is fractional coefficient which depends upon the mass of the molecule. So these equations will decide the movement of charge. It depends upon the electric field applied net charge on the molecule maximum coefficient or depends upon the mass set of the molecule. The rate of migration of ion in the electric field depends upon the net charge of molecules, size, mass, and shape of particles, strength of electric field, properties and supporting medium, temperature of. So these are the different factors affect the rate of migration. So one ion, cation will move towards cathode, anion will be moved to the anode. So this movement depends upon the net charge of the molecule, size, mass, and shape of the particle, strength of electric field, properties of supporting medium, temperature, operation. So factors, what are so these factors will decide a sample. Sample charge rate of migration increases with increase. So if net charge will increase, the migration will increase. Similarly, size rate of migration decreases with larger. So larger molecule will move. So rate of migration decreases with larger molecule. It is due to fractional electricity. Set. The molecules have similar charge but different shape due to parameters. Electric voltage. Increase in voltage leads to increase in rate of migration. So if you increase the voltage, leads to increase in current. Increase in current leads to increase in voltage migration of resistance. Resistance increases migration. So these are the different factors which affect the electron. But for ionic strength, rate of migration increases in higher ionization. Yes, ionization of organic acid increases supporting media. Consumption reduce both rate of migration and consumption separation. Consumption and no species due to presence of Class-2 and so the types of electrophoresis. Zone of electrophoresis, ring boundary control. So, on the basis of zone of electrophoresis, super electrophoresis, pure electrophoresis, molar electrophoresis, cellulose acetate electrophoresis, etc. And if moving by direction, we have capillary electrophoresis, isocapophoresis, isoelectrophoresis, and immunoelectrophoresis. So these are the different types of electrophoresis on the basis of zone electrophoresis on the basis of moving down. So we see one by one instrumentation of general. So when electrophoresis, we should have a power tap, electrophoresis unit, we should have electrodes, but for reservoir supporting electrolysis, it's tampon injector and detector. So these are the total instrumentation like other separation in electrophoresis. General method of operation, so transmission of medium with proper sample application, electrophoretic separation or in. So these are the different mechanism and method of operation of zone electrophoresis. It involves the migration of charged particles on the supporting medium. paper, cellulose, acetate membrane, starches, polyacrylamide, and components separate are distributed into discrete zones on the support layer. Supporting media is saturated with buffer solution. Small volume of sample is applied as a garment on application of PD after end substitute. So these are the zones. So what are the advantages of zone electrophoresis? Useful in biochemical investigation. Cost is low. Small quantity of sample can be analyzed. Easy maintenance. So what are the disadvantages? Unsuitable accurate mobility, isoelectric point determination with the presence of experiments. So these are the disadvantages. So this is paper electrophoresis. You can see here buffer solution will be this anode chamber, cathode chamber, total buffer solution inside the chamber. So this is the paper strip. So on the paper strips, the paper is connected to electrode, cathode and anode. Here mixture would be on the paper roll. It is the form of electrophoresis that is carried out on the filter paper. This technique is useful for separation of small charge molecules such as amino acid and small proteins. So for mixture of amino acid, we can use paper electrophoresis. So it is a form of electrophoresis that is carried out on the filter paper. So we can separate small charge molecules. Filter paper. It is a stabilizing medium. Whatman filter paper we can use. Cellular acetate filter paper we can use. Chromatography paper we can use. So these are the different filter apparatus. Power bank, electrophoretic cell that contains electrodes, proper reservoir, support for paper, transparent insulating sample application. Sample may be applied as a spot uniform. Electrophoretic ground. The current is switched on after the sample has been applied to a paper. Paper has been equilibrated with the buffer. The types of buffer used depends upon the type of preparation. Once removed, paper is driven into detection and quantitative assay. To identify the unknown components in the result mixture, electrophoretically can be used. So physical properties like fluorescence, UV absorption, radioactive exposure. So what means? Fluorescent paper will be in an air, mixture will be cold ordinary. So you could apply the electric current, this will separate. Sample is applied as a circular support on a strip of whiteman paper moistened with the water. So whiteman paper will be moistened with the proper solution. The ends of paper are immersed in a separating reservoir. So each end of paper is immersed in a reservoir of copper in which electrodes are filtered. Upon passing an electric current, the ions in the sample migrates towards the opposite charge particle. The method is suitable for low molecular weight in terms of amino acids. Solution here in paper will be moistened with a water solution. Two ends are dipped in different jars. So one end is anode, another is cathode. When electric power will be on, the charged particles separated with each other. So opposite charge electrodes will attract the opposite charge particles. So in this way we can separate the charge. So gel electrophoresis. It is a technique used for separation of DNA, RNA, protein molecules. So last So this paper electrophoresis is used for amyloidosis and types. So gel electrophoresis is used for separation of DNA, RNA, and protein molecules according to their size and electric charge bring the different apart. So gel is cross-linked polymer whose composition and porosity is suggested based on the specific weight porosity of the target. So what are the types of gel used? Agarose, agar gel, polyacrylamide gel, saphenous gel. So listen, agar gel of a highly purified on charged polysaccharides derived from the agar. Agar is a compound used to separate macromolecules such as nucleic acids larger protein complexes. It is prepared by dissolving 0.5% of agarose in boiling water and allowing it to cool at 40 degrees. Again, because the formation of weakly hydrogen bond and hydrogen bonds. So you can see a overview of Joule electrophoresis step by step. So here I mix the average of buffer. The matrix mixture will be in microwave. Then this will be poured on this tray, and this tray will be charged with the transfer power supply. So these are the total overview of gel. So this page is of focus sodium dudecyl sulfate, a polyacrylamide used in jelly. SDS. So name is SDS. SDS means sodium dodecyl sulfate, polyacrylamide gel. It is the anionic detergent which binds strongly to the so you can see protein SDS complex carries protein SDS complex carries net negative charge and is moved towards the north. Separation is based on the site. So application is useful for protein purification, determine molecular vector protein, quantifying proteins protein application. Process of SDS batch. So these are the different SDS. Boil the sample for 10 minutes to completely denature the proteins. Assemble the gel into the apparatus. Pour the buffer solution into the chamber. Load 20 microliter of sample into the well. After that, run electrophoresis by connecting the current supply. Visualize the batch. So these are the different processes of SDS batch. So thin layer so electrophoresis studies can be carried out in the thin layer chromatography. So here is a layer of sugar, aluminum, and convenient advantage of it is applied for the study of mechanism efficiency combined to cellular synthesis. Acetate electrophoresis it contains three acetyl group first in the chemical and said absorption capacity is less than that of the. So it gives sharper bands. Provides a good diagram for staining glycoproteins. Advantages: no telling of protein. Gives sharp bands and good results. Expensive. Millions of carboxylic residue causes huge electroosmosis. So these are advantages and disadvantages. Principle. So in this alkaline pH will be taken. So you have upper solution will be taken, one unknown cation will be there. So the same alkaline pH, hemoglobin is a negative charge molecule will migrate towards the unknown body. These hemoglobin moves at different rates depending on their nature, which is total controlled by compression of moving boundary properties. The moving boundary method allows the charge species to migrate in free moving surface without the supporting base. Biological active person can be recovered without the use of DNA. Minute concentration of harmful can be detected. Disadvantage. First layer elaborate optic acid molecule. To study homogeneity micromolecular system. Only market. Instrumentation. Consist of a use of glass and rectangular cross section which electrodes placed on one use of the leaves of the so here positive negative use of compounds to the sample solution is included at the bottom to the side upper. So these are not capillary electrolysis. Capillary tube is placed between the two buffer reservoirs and electric field is applied. So what happens? Separation depends upon electrophoretic electroosmosis. So define volume of analyte is introduced into the capillary. So by using capillary neutrophils to 200 micrometer diameter, so you can see on this screen. Higher electric high efficiency. So by using this isotachophoresis. Iso means equal, tacho means speed, magnetic so equal speed of cations and anions is called isotachophoresis. The technique of isotachophoresis depends on the development of potential gradient. So here we can use separation of smaller ionic substance to migrate adjacent contact one, but not over. Sample is not mixed with buffer, hence current flow is carried out entirely by the sample. Isoelectric focusing. Isoelectric focusing, also known as electrofocusing, is a technique for separating different molecules by difference in velocity. It is suitable for separation of unprotected substances. It is type of actually performed on the proteins in a that takes advantage of isoelectric focusing is another method. It is applied in human genetic lab. Separation of soldiers earning immunology, immunoelectrophoresis. So electric field is applied in the study of antigens. So this electrophoresis is used for antigens, antibodies, and any immunoglobulins. Antibodies electrophorically separated, antigens diffuse towards each other and are shifted. It is the detect presence of antibodies here. Immunoglobulins, yours at IgM, IgG, IgA. So what are the processes? The molecules are separated according to difference in their electric charge by electrolysis. Antibody placed in a two but in other antibody diffused towards antigen precipitated with the pressure. So there is another different process of what are applications of electrophoresis in our electrophoresis used in DNA sequencing in the medical research field, in protein research and purification field, in agriculture and testing, in separation of organic acid, alkaloids, carbohydrates, amino acids, alcohol, phenols, in food industry. It is employed in biochemical and chemical fields in the study of protein mixtures such as blood, serum, molecular electrophoresis in combination with autoradiography used to study used for analysis of terpenes, steroids, antibodies, for testing purity of thyroid hormones by joining paper chromatography is used to separate free insulin from plasma protein. Also, it is used for diagnosis of various diseases like kidney, liver, central nervous system, SBSCT. It is used separate sarcoplasma for separation of carbohydrate metabolism. So we have a different uses of application of it. So this is all about electrophoresis. So already we are discussed what is electrophoresis, definition of electrophoresis, how it works. You can see the slide carefully and read it. And this is the definition of elaborately how electrophoresis works. Then these are the factors affecting the electrophoresis. You can see this is the and this is the types of electrophoresis. What are the types of which toxicity is caused, right? The instrument is how this instrument works. Joint electrophoresis. You can see how joint electrophoresis works. So these are advantages and disadvantages of dual electrolysis. So this is very very important paper electrophoresis. The paper and after electrophoresis down. So this is the working of electrophoresis. Other electrophoresis. So total overview of you can see on the slides. SDS electrophoresis. So how SDS, what is the full form of SDS and what is the application of SDS process? So these are the different processes of SDS. Three layer electron. How to watch, what is the advantages. Similar reciprocal electron. So these are the disadvantages. So isotropic process having the same migration capacity. Isoelectroproportion. Immunoelectrophoresis. So it will use in biological pathological process. So this is the application of electrodes. In which case total electrophoresis is used. You can see. Yeah. So we have 15 examples to application. So this is all about separation. Now we'll go to our lesson that separation and separation. In block 1, we have discussed solvent extraction chromatographic methods. Okay, so different chroma. In block 2, we'll study chromatography methods, membrane separation, electrophoresis. This is block 1, block 2. So I think we are going to study section B, while block 3, block 4, block 5. So in block 3, we will study optical spectroscopy, block 5, magnetic resonance spectrometry. So what are in block 3 and so here in block 1 we have unit 1 solvent extraction. Already we have discussed general aspects of chromatography methods. Unit 2 gas chromatography. Unit 3 already we have discussed. Unit 4 high performance liquid chromatography. High performance liquid chromatography. Block 2 unit 5 ion exchange chromatography, size exclusion chromatography, membrane separation. Okay. already we have discussed unit 5, unit 6, 7, 8. So till now we have discussed the electrophoresis of 1, 2. We have discussed it. Next we will go to different spectroscopy methods. So first we will study UV spectroscopy method. So let's start about UV. Yeah, number spectroscopy, chromatography, atomic and emission spectroscopy, proton NMR, two-dimensional, and mass spectroscopy. This is all I start So first of all, I will study first spectroscopic technique, that is UV visible spectroscopy. So UV visible spectroscopy technique. Why we learn UV visible spectroscopy technique? This is the organic liquids with chromophore that observe the most quantitative analytical chemistry and organic chemistry conducted
Good
within
evening,
UV.
sir. Pardon. Hello. Good
Hello?
evening, sir. Good
Huh?
evening, sir.
Yes.
Sir, one request. Can we have the study materials? Could you please send us,
So which group?
sir?
So y- you can give a request to my WhatsApp number so that we can
Sir,
share the
your number, sir?
uh, yes 79, just note it,
Seven
seven
nine.
nine 788
Pardon, sir. Seven.
79788
Okay.
99
Okay.
094.
094 79 788 99 094.
Yes.
Thank you so much, sir.
So we are talking about UV visible spectroscopy. So
Okay.
among any problem? Okay. So UV visible spectroscopic technique. So why we learn UV visible spectroscopy? To detect is there any chromophore or auxotroph present in UV visible spectroscopy. So usually it is used to detect the functional groups present in the organic molecules, detection of impurities present in the molecule. So different qualitative analysis and quantitative analysis. So listen, this is nothing but a UV visible spectrum. So you can see this is an instrument known as UV visible spectrometer, photometer. Where incoming call from Drive Sucheta Sadhu identified by true caller.
Sorry, sir. I was just saving your number.
Okay, no. So this is the UV visual spectrometer. So how do UV spectrometer works? Listen. So we have this arrangement. So through a through a electromagnetic radiation source that will go through a prism. So here beam of splitter and the UV rays will contact with this detector to get the UV. So the ultraviolet and visible absorption spectroscopy is the measurement of attenuation of beam of light after it passes through a sample, which absorption measurement can be at a extremely lower level. So this is UV visible spectroscopy is nothing but electromagnetic radiations of ultraviolet and visible rays is used for this spectroscopy. UV visual spectroscopy is also known as electronic spectroscopy because here electron transitions occurs in the molecular level. So UV and visible radiations are used. These phenomena of interaction of molecules with ultraviolet and visible light. So here we have different electromagnetic radiation, radio waves, microwaves, infrareds, visible, ultraviolet, so many electromagnets. So here in this UV visible spectroscopy technique, we use this ultraviolet region. So listen, ultraviolet and visible region are just before the infrareds. So ultraviolet visible range is from 400 angstrom to 200 angstrom or 200 nanometer to 400 nanometer visible region, then 400 to 800 nanometer is the ultraviolet region. So you can see different region of electromagnetic spectrum. So this is radio waves, microwaves, infrared, visible, ultraviolet, X-ray and gamma rays. So these are different electromagnetic radiations. So we are talking about this ultraviolet and visible region. So this region, electromagnetic radiation, so you can see this ranges from 400 nanometer to 750 or almost 800 nanometer. This visible region. Again, ultraviolet from 200 nanometer, 400 nanometer to 200 nanometer. So these are the region of electromagnetic, ultraviolet electromagnetic. So listen, ultraviolet ranges 190 to 400 nanometer and total visible region are 400 to 800 nanometer. So here we know in visible region there are different colors: Vibra, violet, indigo, blue, green, yellow, orange, red. So red has a more wavelength that is around 800. So these are the different region of different visible organs. So absorption filter when the sample is exposed to light energy that matches the energy difference between the possible electron transition within the molecule. So here we get a lambda max and intensity maximum. So in UV visible spectroscopy, this is the spectrum or spectra of UV visible spectroscopy. So this is the drawn or this is plot absorption versus maximum wavelength. So this is the peak of UV visible spectroscopy. So listen, in y-axis we have absorption, in x-axis we have a wavelength. So here we get a UV visible spectrum. So this is the UV visible spectrum of acetone histamine. So listen, delta max of a isoprene. So isoprene having two double bands here. So you can see this is the absorption peak, this is lambda max. So this is the one sample of UV visible spectrum. Here this molecule will give delta max at 222 nanometer. You can see. So what are the principles of UV visible spectroscopy? Simple. UV visible extends from 200 to 400 nanometer. So in this region, when a light is fall upon a molecule, electronic transitions occur. So this is nothing but a absorption spectroscopy which concern with measurement and absorption of electromagnetic radiation. Every molecule has a bond. So in the molecular level, we have a two orbitals homologous. So HOMO is the highest occupied molecular orbital, LUMO is the lowest unoccupied molecule. So excitation of electrons from HOMO-LUMO occurs. So what are the possible electronic transitions occurs in UV visible spectroscopy? That's it. So listen, UV spectroscopy is a concern with the study of absorption of UV radiation which ranges from 200 to 400 nanometers. So here valence electron absorbs the energy and they will excited to excite. So this molecule, when a molecule is formed, it has sigma orbital, pi orbital, so non-bonding orbital. So sigma has a bonding and anti-bonding. So sigma electrons present in saturated compound, pi electrons present in unsaturated, n electrons in non-bonding. So listen. So these are the possible electronic transition across within a molecule. So here sigma electron can jump to sigma star. So sigma is the bonding, then pi bonding, then non-bonding, then anti-bonding pi star. So this is pi star. So sigma has lower energy, sigma star has higher energy. Pi is a bonding, then pi star anti-bonding. So this is non-bonding. So we have sigma, pi, non-bonding, pi star, sigma. So we'll have a transition sigma to sigma star, pi to pi star, n to pi star, n to sigma star. So these are the possible electronic transition across in every universe. Listen. So we have actually six transitions can possible. So among them, transitions are following. So you can see n to pi star possible, n to but pi to pi star possible, but pi sigma to sigma star, sorry, pi to sigma star or sigma to pi star. This is not possible for me. Why? We'll see in the minute. So listen, what are the types of transition? So sigma to sigma star, n to sigma star, n to pi star, pi to pi. So which type of organic molecule shows this type of spectroscopic pattern? So six are possible. The last five and six are not a theoretical possible, but practically this is forbidden transition. This transition not occur. So sigma to sigma transition occurs when an electron in a bonding sigma orbital of a molecule excited to corresponding anti-bonding orbit by absorption of radiation. Sigma to sigma transition occurs majorly in alkene molecules. Because only sigmas are possible in saturated hydrocarbons. So here we'll see due to sigma transition we get a lambda max 125 nanometer. So where sigma to sigma transition possible in a methane or CH bond only, where saturation of bonds are required. Similarly, sigma to sigma star transition, we have a different. So we talk about pi to pi star. Here pi bond should be present. So here alkene and carbonyl nitride where all saturations are means more than one bond will be there. Pi electron in a bonding orbital is excited to corresponding anti-bonding orbital pi star. Compounds containing a multiple bonds like alkenes, alkynes, carbonyls, nitriles, etc. where pi to pi transition. Alkene generally absorb in a region of opposite. So in alkene type of molecule, we'll see pi to pi star transitions. So pi electron in a bonding orbital is excited to corresponding antibonding site. So pi electron comes to pi. So these transitions can be seen in multiple bands like alkane, alkynes, carbonyls, nitriles, etc. So what about the N to sigma star transition? Saturated compounds containing atoms Lone pair electrons like oxygen, nitrogen, sulfur, halogens are common. N2 sigma structure. The condenser usually equals less sigma to sigma structure. Number of organic molecules. So N to N means unpaired. Unpaired electron present in oxygen, nitrogen and sulfur like atoms. So here the compounds which contain non-bonded electrons and sigma bonds. These compounds are alcohols, amines, iols, etc. So we'll see both N to sigma star and sigma to sigma star also. So N to sigma star transition saturated compounds containing atoms with lone pairs, non-bonding electrons are capable of N to sigma star. This transition usually need less energy than the sigma to sigma star. So here this type of transition occurs in case of alcohols, amines, ions, etc. So you can see, so this transition approximately 1 to 50 to 250. The last and most importantly aim to pass. So both lone pair will be there, pi bond will be there. So these are compounds are carbonyl compounds, nitriles, nitrous compound, etc. So this type of transition. Here an electron from non-bonding orbital is converted to anti-bonding particle. The compounds containing double bond involving heteroatom C double bond O, C triple bond A, N double bond O to both sides. N to pi star transition require minimum so absorption of the number. So these are the simple transition occur in equilibrium. So already we have seen first sigma to sigma stars, then pi to pi stars, n to pi star, n to sigma star. So these are the different transitions occur in EV visuals. N to pi star transition has minimum energy, high wavelength. So this is the most frequent and most visible delta mass or transitions. Of course, in carbon nitrogen around 300. So what about 5 and 6? Sigma to sigma star and pi to sigma star is a forbidden and not allowed, theoretically possible, but actually when to pi star, pi to pi star, electron transfer is a region of working which is forbidden. So you can see n to sigma star, pi to pi star transition, and so n to pi star, pi to pi star, rigid data. So you can see these are the transitions occur in EV videos. So first is sigma bond, then pi bond. So sigma is the bonding, sigma star is the antibond, higher energy. Pi bonding, then pi star. And in between we have n non-bonding. So when electron transition observe, so transition can occur from sigma to sigma star. So sigma to sigma star transition occurs in which type of organic molecules? Alkanes. Because in alkanes we have only saturated bonds. So this is a saturated hydrocarbon where we can get only sigma molecule around. Similarly, pi bonds, pi to pi star observes in alkynes type of. Similarly, N is a non-bonding electron, like oxygen, nitrogen, sulfur atoms we get non-bonding. So N to sigma stars occurs in thiol, amines, halocopper, halocoppers, etc. So here pi to N to pi stars occurs in carbonyl compounds, nitriles, etc. So these are the different. So among these, sigma to sigma star transition in the high energy gap. Sigma to sigma star gap is more. So similarly, pi to pi star transition is little bit less than sigma to sigma. Then we'll go to N. So if we look at the energy, increasing order, decreasing order of energy of absorption of electronic transition. So you can see here. So C double bond C chromophore will be there. So we'll see in ethene molecule here N to pi to pi star transition possible. It will shows delta max maximum in 170. C triple bond C hexane pi to pi star transition possible here 180 nano. Similarly, in carbonyl compounds, N to pi star, pi to pi star transition possible, so we get delta max nitrogen. So these are the organic functional groups or chromophores. Here are the example of compound. So which type of transition we can observe in this type of? So if we look at the electronic transitions, we have among six, four as possible. So which has more energy? Sigma to sigma star transition has more energy. Then we have to sigma to pi star, sigma, then pi to sigma star, then n to sigma star, pi to pi star. N. So we have a different energy here. So sigma to sigma star has more energy. Then we can see pi to sigma to pi star, sigma to pi star. Then we have to n to sigma star. Then we have pi to pi star. So these are the energy electronic transition of absorption. So electronic transition occurs usually HOMO to LUMO. HOMO is the highest occupied molecular orbital where electron can jump from HOMO to LUMO, from occupied or occupied. So you can see so in individual spectroscopy, we need individual electromagnetic and visual electromagnetic radiation. So we see different electronic conditions. So this is the UV visible and this is the UV visual spectrophotometer. You can see. So UV visual spectroscopy like that. So these are the region of UV visual spectroscopy. So these are the ultraviolet from 200 to 400. So you can see the graph of the absorption spectroscopy, UV visible spectrum of acetone, and this is UV visible spectrum of isoprene. So this is the different principle of UV visible spectrum. So let's check the electronic transition. Here we have transition sigma to sigma, pi to pi, and then to sigma star. So these are possible electron transition in the you can see sigma to sigma star transition possible in orchid, n to pi sigma star possible in case of ions, amines, chloroalkyl halides, n to pi star transition possible in carbonyl compound, pi to pi star transition possible in alkane compounds. The last 5.6 are forbidden. So this ends and task transition is very important transition because this transition has low energy, high wavelength. So high wavelength we can see in the video spectrum very clearly. So you can see different transition. So if you look at this slide, so different transitions of sigma to sigma star energy level. So you can see sigma to sigma star transition have more energy than pi to pi star transition. Then n to sigma star transition. Then n to pi star transition. So these are all equals you can see different transitions. So we want to monitor the transition across cytosol. So the same thing we discussed introduction part of the so we can so this things we use spectroscopy, IR and Raman spectroscopy colorimetry and phosphometry, atomic anisotropy, magnetic resonance, dynamic, dynamic, high resolution, mass spectrometry. All these things we discuss in the next class. We have two class ended. We'll wind up our class here. We'll see you in the next class. Thank you very much.